Hello everyone. I'd like to thank you for coming to my presentation on my work towards 2D materials as quantum nano-electromechanical systems and proposed research. I'd like to extend a special thank you to Graham Gibson for his help at NFK, Kevin McElhaney for his AFM support, and Rob Noble for his guidance. My objectives are to create a nano-mechanical resonator using 2D materials. I want to measure the zero-point oscillations of this resonator in its ground state. I believe I can then explore quantum mechanics and probe material properties with this experiment, and I believe it will lay groundwork for further device development. First, some background. 2D materials are atomically thin materials. The most famous of these is graphene, but there are others, such as hexagonal boron nitride, niobium diselenide, and molybdenum disulfide. The properties of 2D materials are diverse. Of these materials I've listed here, graphene is a semi-metal, HBN is an insulator, niobium diselenide is a conductor, and MOS2 is a semiconductor. However, one of the features of 2D materials is that their properties change as they approach atomic thickness. And some of these properties can be exotic. For example, niobium diselenide becomes a superconductor when it is less than 10 layers thick. Another feature of these materials is that they can be easily prepared via mechanical exfoliation, which is using tape to separate the layers of material. The layers of material are easily cleaved as they are only held together by weak van der Waals forces. It is possible to stack layers of 2D materials to create heterostructures, which we call van der Waals heterostructures. As we stack, we can either vary the material or the positional alignment between the layers. This can produce a material with desirable properties. The image at the right here shows how we can stack different materials like different colored Lego bricks. There's been a lot of interest recently in twisted structures, where there's a rotational misalignment between the layers. In 2018, twisted bilayer graphene was found to superconduct when the layers are offset at a 1.1 degree twist angle. Now, let's try not to get hypnotized by the image at the bottom right. One of the interesting consequences of rotational misalignment is the creation of a moire superlattice. A moire superlattice is a long-range periodic modulation caused by the crystal lattice interaction between layers. What happens is that the translational symmetry of the original lattice is broken. The breaking of translational symmetry and introduction of long-term periodic modulation affects the band structure of the material. So to highlight what is truly interesting is that the appearance of this moire structure creates low-energy subbands, and it is these bands that are responsible for the exotic properties at special angles. The image on the left here shows what a moire pattern may look like in a heterostructure, and the image on the right shows us how the pattern can change with rotation angle. The image in the top right up here shows how the individual atoms in different lattices can be spaced differently according to the rotational offset. So this shows that the rotational offset affects the distance between the atoms. Some of my work so far has been spent trying to exfoliate crystals and attempting to produce large, pristine monolayers. For those that are not familiar, a layer of graphene is only one carbon atom thick, which is less than a nanometer. Now I need these large, pristine monolayers because to create a resonator from the heterostructure, I have to have large, clean, single atom thick flakes. So to make these samples, we use tape to mechanically peel the layers apart. The tape contacts the bulk material and lifts some flakes from the bulk. And then by pressing the tape to a new substrate, we hope to leave behind some flakes from the original material. This sounds simple, but producing and finding these samples can be tricky because being only an atom thick, they appear very faint and it takes some time to learn how to identify them. Our process is to search silicon oxide substrates optically with a microscope. These flakes appear different colors due to their interference with the reflected light. Once we find a suspected monolayer flake, we then measure its height with an AFM. After we are sure that our flake is monolayer in thickness, we then try to build a heterostructure. So here's an image of a graphene flake I produced while experimenting with a new exfoliation technique. I used graphene thermal release transfer tape to exfoliate a bulk crystal and placed the transfer tape on silicon oxide, and then heated the tape to release the crystals. As you can see from the image on the left, there's some adhesive that is being left behind when we remove the tape from the substrate. Now, I was able to clean some of this adhesive off, and this can be seen in the image here at the right. Now, using this method, I've been able to produce flakes up to 50 microns in size. These AFM images are the same flake from the previous slide. The image on the left here is from before the cleaning process, and the image on the right is from after cleaning. These little white dots we believe to be deposited adhesive. They're not visible in the original optical image just because they're so small. The image on the right shows the flake after cleaning, and we can see that the substrate is devoid of any little white dots. So that means that the substrate is actually being cleaned quite well. The large blob has been removed. However, the flake still has some white dots, which means that either adhesive is still on the flake or that there's adhesive under the flake. I'm continuing to develop this method, and I've been able to produce cleaner flakes, albeit with more cleaning. I'm also continuing to work with other methods that require less cleaning and thus less chemical exposure to my samples. Once we have our flakes ready, we begin to stack them. Been working on a placement technique called the hot pickup method. In this method, we first spin coat a layer of PPC, or polypropylene carbonate, on a layer of PDMS, polydimethylsiloxane. The resulting polymer jelly is then placed on a glass slide. Now we then flip this glass slide upside down, which you can see here, and we align it over a sample of HBN. We then bring the samples into contact, heat, cool, and release. And this process picks up this HBN flake. We then replace the HBN sample with a graphene sample, and we align the HBN over the graphene, bring in the contact, and slowly release while hot. The PPC passes through a glass transition, and we can gently release the HBN onto the graphene. Then we can repeat this process to pick up the HBN, the graphene attached, as you can see in this image. The AFM image on the right here shows a graphene flake that I've picked up using this HBN flake. Now, it looks like it's sitting here a little precariously, and it is because it's drooping over the edges of the HBN. Beneath is our PPC PDMS glass slide substrate. So let's do some more background on the NEMS circuit we would like to fabricate. Now, an object that resonates with well-defined frequencies we can define as a resonator. This is comparable to a harmonic oscillator, but it can be driven to resonate at specific frequencies according to mode. At the nanometer scale, we call this a nanomechanical resonator. Inductor capacitor circuits have been well studied. They're widely known as LC circuits or tank circuits, and they are often used in radio because they have a very well-defined resonant frequency. If we create an inductor capacitor circuit out of a superconducting material, then we would expect no resistance. We can create one plate of our capacitor out of a 2D material, as you can see here. Now, as charge builds up across the capacitor, the flake will move, and this produces what is called a variable capacitor. We can thus couple the mechanics to the electronics and create a coupled electromechanical system. So let's look quickly at a simplified version of the problem. We'll assume that the 2D material is located at distance d above the lower electrode, and that the distance it oscillates is a value z. This circuit will have a resonant frequency, as I've said already. If an AC signal at resonance is placed near the inductor L, a current is induced on the wire and charges will flow towards the capacitor. The electrical oscillations will obey this first equation. The potential across the capacitor produces a force on the flake, which causes it to move the distance z. The motion of the flake is then described by this second equation. Now, the change in distance produces a change in capacitance, which is represented by this third equation. And as we can see from the third equation, when the value of z is close to d, the coupling is going to be very strong. But how will we measure this motion? The change in capacitance will affect the resonant frequency, and thus by measuring the change in the drive signal, we can measure the change in the resonant frequency. This experiment has been performed before. In 2010, John Teufel made this NEMS circuit with an aluminum resonator and was able to successfully place it in its ground state with sideband cooling. My goal is to perform the same experiment, but with a drum made of superconducting 2D materials. Since 2D materials are flexible, thinner, and have less mass, I expect the motion to be significantly larger. So our planned device is a heterostructure made of 2D materials that is very thin, very light, and superconducting. Having a high mechanical quality factor and a high circuit quality factor will help with the measurement, as little energy is lost from the oscillations. Some candidate structures are graphene encapsulated niobium diselenide and twisted bilayer graphene. So our planned experiment is that we want to measure the zero-point motion of a resonator. The zero-point motion is the quantum fluctuation of an object due to the Heisenberg uncertainty principle. So we plan to lower the temperature of our resonator cryogenically using a dilution refrigerator. We will then use a technique called sideband cooling to put the resonator into its ground state by removing the phonons, or vibrations, from it. We will then couple a microwave drive signal to the LC circuit and measure the power spectral density of the microwave drive. The LC circuit will couple to the drive signal at resonance, and the resonance will change according to the motion of the flake. And we can then read out the flake's position. At this point, it should be noted that the research we had planned was put on hold due to COVID. I had to pivot what I was doing and work on simulations. So my questions were, how can we model a 2D drum in a 3D space? And if I consider the full 2D geometry, are there any solutions that already exist? What are their equations of motion? Well, I found out that if I know the first mode shape, then I can figure out everything else. And so what I did is I first considered, what if this acts like a plate where there's little stress or strain in the system? Thin plates can be modeled to study the deformation of a rigid material. And as our suspended flakes are stretched across, this can be a first assumption. So the plate deflection profiles can be approximated with a quadratic curve if the maximum deflection is known. However, I quickly learned that thin plate approximations, this green line here, vastly overestimate the deflection. Now, there is a more appropriate solution, which is an energy approximation, which is valid for finding the maximum deflection of these thin plates. And that is represented by this blue curve here. And yes, it is a curve. The blue curve from the previous slide is this blue curve here. This is the energy approximation. Now, to think about limiting behaviors, I then looked at what if strain dominates the system? Well, if strain dominates, then we have this curve here. And this is a linear membrane, which is represented by a Bessel function. This teal curve represents what happens when there's no initial strain, but as the deflection is increased, strain begins to quickly take over the behavior. And this is called a nonlinear membrane, which obeys the Flaupel-von Karman equations, which are notoriously difficult to solve. I also compared what happens when we have a static electrostatic force versus a coupled electrostatic force. The blue curve here is the energy approximation where an electrostatic force is applied, but it's constant. So as the flake deforms, the force doesn't change. Whereas this orange one is a coupled electrostatic force, which the force gets stronger as the flake deforms and is attracted to the other electrode. After examining these analytic approximations, I built models using the finite element analysis software COMSOL. The COMSOL models were able to reproduce the analytic solutions with a mixture of clever meshing and adjusting the settings. Now, this leads me to the conclusion that COMSOL can be used to model flake deformations, as it agrees with the analytical approximations of simple geometries, but it can also handle much more complex geometries. So my next steps are to continue my modeling in COMSOL by building more complicated models. I would like to eventually model an actuated drum and eventually progress up to a full circuit. I'm also beginning to work more with the niobium diselenide material, which I will concurrently use as I'm working with trying to build a twisted bilayer graphene sample. I'm also beginning to look at ways to improve our optical analysis and beginning to explore suspension techniques. I'd like to again thank you for coming to my presentation, and I'd again like to thank my group members and Robert Noble for his ongoing support through this journey. Thank you.